Hello everyone. Today I'll explain to you all pay shortest path algorithm, which is solved using dynamic programming. The objective of this problem is to find the distance shortest path between every pair of vertices in the given graph. So here is a graph given with 4 vertices, and we need to find the shortest distance between every pair of vertices. Now you might, by the name all pay shortest path, you can recall the problem which we have solved previously, that is single source shortest path algorithm, wherein we were finding the distance between a single source to all the other vertices of a given graph. But here in this case, we are finding the shortest path between all the pairs of the vertex, all the pair of vertex in the given graph. Now we know that dynamic programming always says that problems should be solved by taking sequence of decisions. So here we need to take decisions whether a shorter path exists between any pair of two vertices that is given. So we'll find all the distances or the shorter path between the pair of vertices that goes via vertex 1, vertex 2, vertex 3 and vertex 4 in this case, because there are 4 vertices here. Now for this we can make use of an adjacency matrix, and let us say that the initial adjacency matrix is represented here. This is my column number and row number which is highlighted. Now with this graph, there is a directed graph that is given. There is no self loop from 1 to 1. So the distance from 1 to 1 is 0. Now 1 to 2, there is an edge that is costing. The cost is 8. So I have mentioned here from 1 to 2, the cost is 8. Now 1 to 3. 1 to 3, you don't have an edge. Please make sure, since it is a directed graph, there is a path from 3 to 1, but there is no path from 1 to 3. So in this particular cell, from 1 to 3, we will write infinity because there is no path. Now 1 to 4. 1 to 4, the path cost is 1. So we have written the cost is 1 here. Similarly from 2 to 1. 2 to 1, there is no edge, but 1 to 2 there is an edge, but 2 to 1 there is no edge. There is a directed graph. So it is marked as infinity. 2 to 2 is 0, and 2 to 3 we have an edge with cost 1. 2 to 4 we don't have any edge, so it is marked as infinity. Similarly, fill the adjacency matrix with the cost that is given in the graph. If there is no edge between two vertices, mark it as infinity. The weight from the vertex to the vertex itself is 0. So the diagonal elements are 0 here. Remaining elements you can fill. Now we have the initial adjacency matrix. Now our objective is to find if there is a path exists between pair of vertices through other intermediate nodes. For that we will construct a new adjacency matrix which says that find all the cost of the path wherein we can pass through one. Taking 1 as an intermediate vertex, let us find if there exists a shorter path between any two pair of vertices. That is, from 2 to 3 I have the cost is 1. Now I would like to check if there exists a path from 2 to 1 and 1 to 3 such that I get a shorter cost. Or I have 1 to 8, sorry, yeah, I have a path from 4 to 3. Now I would like to check whether there is a path from 4 to 1 and 1 to 3 such that the distance can be, I can find a shorter distance. Okay, in order to do that, first we'll redo the adjacency matrix which says that passing through one, whether you can find a shorter path. Whenever you move forward, we will take the previous adjacency matrix that is computed. So in this case, this is the initial adjacency matrix with respect to the weight of the graph given. In the next stage, whenever you are calculating A1 indicate that I am trying to find if there is a shorter path that exists when the intermediate vertex is 1. Okay, we will refer to the previous matrix when we are working with A1. So let's see, this is our initial matrix. We will see whether we can find a shorter path through 1. Now when I say through 1, we will retain the diagonal elements as 0. So you need not compute 0. So diagonal elements are always 0. So we will enter diagonal elements. One more thing we need to take care is, since it is passing through 1, the elements of the row 1 and the column 1 will remain as it is. Because if I want to say I already have a path from 2 to 1, and now I am saying find a path from 2 to 1 where the intermediate vertex is 1. There will be no change. Similarly, when I say I have already a cost from 3 to 1 as 4, and I want to find an intermediate including the intermediate vertex as 1, and find the cost from 3 to 1 and 1 to 1, it will be the same. So the rows and the column of 1 can be retained as it is. We will find remaining weights whether we can find a shorter weight or not. The remaining are these. Just mark it. I'll use a pointer and a highlighter here. Okay. Since it is through 1, I can retain the values in A0 in the row 1 as well as in the column 1 and the diagonal elements. Only the remaining value I need to check. Okay, so the part highlighted we need not check. Let us find remaining. Now I have a cost from 2 to 3. I say that the path, okay, so I'll say that the path from 2 to 3 is 1. Now what is that I need to do? I need to find if there exists a shorter path where I can include an intermediate vertex as 1. So if there is a path from 2 to 3 and I include an intermediate vertex as 1, what will I get? A of 2 to 3. I'm including the intermediate vertex as 1. So I'm trying to find if there is a path from 2 to 1 and 1 to 3. So it will be A of 2 to 1 plus A of 1 to 3. Let's see what is A of 2 to 1. A of 2 to 1 is infinity here. What about A of 1 to 3? 1 to 3 is again infinity. Now I need to come A of 2 to 3. A of 2 to 3 is 1. So I need to compare between 1 and infinity plus infinity. Which is smaller? 1 is smaller. Which was the initial weight. So I am retaining it. I am not making any change to it. Now we'll go for the next one, that is 2 and 4. So there is an edge from 2 to 4 where the cost is infinity because I don't know the value of the cost. Now I need to find if there is a path that exists from 2 to 1 and 1 to 4. That is A of 2 comma 4. I am checking if there is a path from A of 2 to 1 plus A of 1 to 4. Let's check. A of 2 to 1, between 2 and 1 it is infinity. So A of 2 to 1 is infinity plus A of 1 to 4. 1 to 4 is 1. And A of 2 to 4 is infinity. So I'm checking which is smaller, infinity or infinity plus 1. Infinity, so I retain it as infinity. Now we'll go to this case, that is A of 3 comma 2. So what is that I need to check? I need to check if there exists a path if I add an intermediate node as 1 between 3 to 2. So when I add an intermediate node as 1 between 3 to 2, what do I get? 3 to 1 and 1 to 2. So that is here. So A of 3 to 2 can be represented as A of 3 to 3 comma 1 plus A of 1 comma 2 when I am adding an intermediate node as 1. Now I am checking if there is a path. A of 3 comma 2. A of 3 comma 2. What is that? Infinity. Right? So that is infinity. And A of 3 comma 1. 3 comma 1 is 4. So I'll write 4 here. And A of 1 comma 2. A of 1 comma 2 is 8. So I'm checking between infinity and 4 plus 8. 4 plus 8 is 12. Which is smaller? 12 or infinity? 12 is smaller. So I will change this value, that is A of 3 comma 2 to 12. What is the meaning of that? When I add an intermediate node 1, that is there exists a path between 3 and 2 through 1 which is a shorter distance than direct 3 comma 2. Let's look into the graph once. So I was trying to find the distance between 3 and 2. 3 to 2 there was no edge because it is a directed graph, and 3 to 2 there was no edge. So I marked it as infinity. Now I am trying to check whether there is an edge from 3 to 1 and 1 to 2 so that the path is less than infinity. So we can see here 3 to 1 it is 4, 1 to 2 it is 8, so it is 12. 12 is less than infinity. That is the reason I am changing this value to 12. Now this I need not check, I'll go for this. 3 to 4. 3 to 4 initially the value is infinity. It means that there is no direct edge from 3 to 4. But we are trying to check if there is an edge from 3 to 1 and 1 to 4. That is what is done here. A of 3 comma 4, we are adding an intermediate node, that is A of 3 comma 1 plus A of 1 comma 4. A of 3 comma 4, 3 to 4 is infinity. A of 3 comma 1, 3 comma 1 is 4. A of 1 comma 4, 1 comma 4 is 1. So you'll get 4 plus 1 is 5. 5 is of course less than infinity. So we will replace this value, that is A of 3 comma 4 by the new value whatever we have got, a shorter distance whatever we have got is 5. Now we'll go for the next, that is 4 comma 2. 4 comma 2 I'm checking with A of 4 comma 1 plus A of 1 comma 2. A of 4 comma 2, what is that? It is 2. 2 I am checking against A of 4 comma 1 plus A of 1 comma 2. 4 comma 1 is infinity, 1 comma 2 is 8, infinity plus 8. Of course 2 is smaller, so I am retaining the value of 2. Next I should check for A of 4 comma 3. A of 4 comma 3 is A of 4 comma 1 plus A of 1 comma 3. A of 4 comma 3 is given here 9. A of 4 comma 1 is infinity. A of 1 comma 3 is infinity. So 9 and infinity, if you compare, 9 is smaller. So I am retaining the value of 9. So I got a new matrix when I am passing through 1, keeping 1 as the intermediate vertex. Now let's move forward. We'll see the adjacency matrix when 2 as the intermediate vertex. So for this, I need to refer back to my previous adjacency matrix, that is 1, whatever newly I have calculated. Now when you consider A of 2, that is the adjacency matrix with respect to 2, what is that I retain? I will retain the diagonal elements as 0, right? And whatever is the column associated with 2 or a row associated with 2 as well as the column associated with 2, I will retain in my new adjacency matrix. So infinity 0 1 infinity I'll write as it is, infinity 0 1 infinity, and 8 0 12 2, 8 0 12 2 I will write as it is, remaining I will calculate. So what is that I need to calculate? I need to calculate this value, that is 1 comma 3. So A of 1 comma 3, my intermediate vertex now is 2. So I need to find a path. If there exists a path, A of 1 comma 2 plus A of 2 comma 3. So I can see 1 comma 2 is 8, 2 comma 3 is 1. So 8 plus 1, 9. 9 is of course smaller than infinity. So I'll change the value of this from infinity to 9. Now I'll go for the next value, that is 1 comma 4. 1 comma 4 is A of 1 comma 2 plus A of 2 comma 4. A of 1 comma 4 is 1. A of 1 comma 2 is 8. A of 2 comma 4 is infinity. So 1 and 8 plus infinity I am comparing. Smaller is 1. So I'll retain the old value 1. Now next value I have to find is A of 2 comma 1. No, I need not find that because this is in the same row of 2. I need not find. Next value I need to find is A of 3 comma 1. A of 3 comma 1, intermediate vertex is 2. So it is A of 3 comma 2 plus A of 2 comma 1. 3 comma 1 is 4. 3 comma 2 is 12. A of 2 comma 1 is infinity. 2 comma 1 is infinity here. Smaller is 4. So the 4 value is retained. Next I have A of 3 comma 4. 3 comma 4 is 5 initially. I am finding if there is a new path that exists. A of 3 comma 2 plus A of 2 comma 4, 12 plus infinity, smaller is 5. So this 5 is retained here. Now I am finding A of 4 comma 1, that is A of 4 comma 2 plus A of 2 comma 1. 4 comma 1 is infinity, 4 comma 2 is 2, and 2 comma 1 is infinity. When you compare this, infinity itself is, I'll have to retain this value as infinity because I'm not getting any smaller path. Now this 9, I have a value 9 here for 4 comma 3. So I am trying to check by whether there exists an alternative path through 2. So A of 4 comma 3 equal to A of 4 comma 2 plus A of 2 comma 3. 4 comma 3 is 9 here. 4 comma 2 is 2 and 2 comma 3 is 1. So what do I get? 9 and 3 I need to compare. Smaller value is 3. So in this place of 9, I write 3 in the new adjacency matrix. So I've got a new adjacency matrix. This adjacency matrix, I'll use it for the next, finding the next shorter path. So here again. Now when you are taking 3 as the intermediate node, what is that you will retain as it is? Diagonal elements I'll retain. This row I will retain. The row number 3 and the column number 3 I'll retain. I'll have to find the remaining values. So let me color it so that we will not have to use it. Okay. So the diagonal elements I need not look into, and the row 3 and column 3 I can retain as it is. So I need to find this now, a of 1 comma 2. My intermediate node is 3. So how do I find a of 1 comma 2 equal to a of 1 comma 3 plus a of 3 comma 2. So I'm finding if there is a shorter path. A of 1 comma 2 is 8. A of 1 comma 3 is 9 and a of 3 comma 2 is 12. Which is smaller here? 8 and 9 plus 12. Of course 8 is smaller. So I'll retain this value here. Next value I have to check is 1. That is 1 comma 4. A of 1 comma 4 with 3 as the intermediate node will be a of 1 comma 3 plus a of 3 comma 4. So a of 1 comma 4 is 1 and a of 1 comma 3 is 9. A of 3 comma 4 is 5. So 1 and 9 plus 5. 1 is smaller. So this value will be retained in the new adjacency matrix. Now we will check for this a of 2 comma 1. Intermediate node is 3. So I should check whether there is a path from a of 2 comma 3 and a of 3 comma 1. That is mentioned here. A of 2 comma 1, I need to check whether there is a path from a of 2 comma 3 and a of 3 comma 1, where 3 is my intermediate node. Now a of 2 comma 1, here it is infinity. A of 2 comma 3 is 1. A of 3 comma 1 is 4. Right? So infinity and 1 plus 4, which is smaller? 1 plus 4, that is 5, is smaller. So I need to replace this value, that is a of 2 comma 1, by the new value which I received, a shorter path, that is 5. So it is been replaced. Next we will check with this value, a of 2 comma 4. So we are checking if there is a path from a of 2 comma 3 and then from 3 comma 4. So a of 2 comma 4 is infinity, a of 2 comma 3 is 1, a of 3 comma 4 is 5. So I am checking if there is a path from a of 2 comma 3 and a of 3 comma 4 which is smaller than the distance whatever available between a of 2 and 4. Now we'll have infinity and 1 plus 5. 1 plus 5 is 6. 6 is less than infinity. So this infinity will be replaced by the new shorter path which we have found, which is through 3. That is 2 to 3 and 3 to 4. We got a shorter path, that is 6. Now this row we need not check. We need to check this value. That is 4 comma 1. When the intermediate node is 3, we will have to check whether there is a path from 4 to 3 and then from 3 to 1. So we are checking it here, 4 to 3 and 3 to 1. A of 4 comma 1 is given infinity in the adjacency matrix. A of 4 comma 3 is 3 and A of 3 comma 1 is 4. So we are comparing between infinity and 3 plus 4. 3 plus 4 is 7. So which is smaller? 7 is smaller. So this infinity will be replaced with 7 as the shorter path through the vertex 3. Now we'll have to check for this. A of 4 comma 2. A of 4 comma 2, we are checking if there is a shorter path from A of 4 comma 3 and then from 3 comma 2. A of 4 comma 2 is 2. A of 4 comma 3 is 3 and A of 3 comma 2 is 12. So between 2 and 3 plus 12, 2 is smaller. So this is retained as it is in the new adjacency matrix. Now we have got an adjacency matrix with respect to 3 as the intermediate node. This new adjacency matrix, we'll use it for the next calculation. So herein we have the next set of calculation where we are finding the adjacency matrix for the node which is passing through 4. So we are not considering the diagonal element, and since we are considering 4 as the intermediate vertex, we need not consider the column 4 and the row 4. Okay, the remaining element we need to check whether there is a shorter path. So first one is 1 comma 2. So what is that? What is our intermediate node here? Intermediate node is 4 here. So between 1 and 2 there is an edge with cost 8. So we are checking if there is any shorter path from 1 to 4 and 4 to 2. So that is what we are calculating here. A of 1 to 2, if there is any shorter path between A of 1 to 4 and 4 comma 2, 4 being the intermediate node. 1 comma 2 is 8. It's given here. 1 comma 4 is 1 and 4 comma 2 is 2. So you are comparing between 8 and 3. 3 is smaller. It means that this 8 can be replaced with a shorter distance if we are moving through the vertex 4. So 8 is replaced with 3. Now we'll go for the next element, that is 1 comma 3. 1 comma 3, intermediate node is 4. So we are checking is there is any easy path or the shorter path from 1 to 4 and from 4 to 3. So A of 1 comma 3 given here is 9 and A of 1 comma 4 is 1. 4 comma 3 is 3. So which is smaller here, 9 or 1 plus 3? 1 plus 3, that is 4. Hence we can conclude that this 9 can be replaced by a shorter path which is equal to 4. Now we need to check with this 5, 2 comma 1. A of 2 comma 1, we are trying to check if there is a path from 2 to 4 and 4 to 1 which is shorter than 5. A of 2 comma 1 is 5. A of 2 comma 4, 2 comma 4 is 6 from here. A of 4 comma 1 is 7. So which is smaller? 5 is smaller. So we need not change. We'll retain it. Now this one, that is A of 2 comma 3. A of 2 comma 3, we are checking if there is a shorter path from A of 2 comma 4 and then 4 comma 3. By looking into this, we'll know that it is a minimal path cost, that is 1. But still we'll check. A of 2 comma 3 is 1. A of 2 comma 4 is 6 here. A of 4 comma 3 is 3 here. So 1 and 6 plus 3. 1 is smaller. We are retaining it. Now we will try with 4. That is A of 3 comma 1. So we are trying to check whether there is a path through an intermediate vertex 4. A of 3 comma 4 plus A of 4 comma 1. A of 3 comma 1 is 4. A of 3 comma 4 is 5. And A of 4 comma 1 is 7. Which is smaller? 4 is smaller. So we are retaining it. Now next we have is this particular value 12. A of 3 comma 2. A of 3 comma 2 with intermediate vertex, we are checking whether there is a path from A of 3 comma 4 and A of 4 comma 2. So A of 3 comma 2 is 12. A of 3 comma 4 is 5. A of 4 comma 2 here is 2. So between 12 and 5 plus 2. 5 plus 2 is smaller. That means there is a shorter path from 3 to 4 and 4 to 2 instead of directly from 3 to 2. So we will replace this 12 here by the new value what we have got here, that is 7 in the new adjacency matrix. Now if you notice, that's all, only 4 nodes we had. We have found all the paths or the shortest path between any two pair of vertex. So we can see between 1 and 1 the shortest path is 0, 1 and 2 shortest path is 3, 1 and 3 shortest path is 4, 1 and 4 shortest path is 1. Similarly 2 and 1 shortest path is 5, 2 and 2 it is 0, 2 and 3 the shortest path is 1, 2 and 4 shortest path is 6, and 3 and 1 shortest path is 4, 3 and 2 shortest path is 7, 3 and 3 shortest path is 0, 3 and 4 shortest path is 5, 4 and 1 it is 7, 4 and 2 is 2, and 4 and 3 is 3, and 4 and 4 is 0. Hence we have concluded the shortest path between all the pair of vertices. That's all for all pair shortest path. Thank you so much.